AMT Powerplant, Chapter 101 Aircraft Engine General Requirements. Hey everyone, let's dive into how aircraft engines work and what they need to keep those planes soaring. Picture an airplane cruising through the sky. How does it manage to stay up there? It's all about thrust. Whether it's to lift those wings or combat gravity during takeoff, thrust is what keeps planes flying smoothly. But here's the thing. For a plane to stay level, the thrust it generates has to match and oppose the drag working against it. And where does this magical thrust come from? Enter the aircraft heat engine. These engines are like magicians, converting heat energy into mechanical energy by flowing air through them. But they release this energy at a point where the pressure is higher than the surrounding air pressure. Thrust, in simple terms, happens when air is pushed in the opposite direction to where the plane is headed. It's all about Newton's third law. For every action, there's an equal and opposite reaction. So as air gets pushed back, the plane moves forward. But here's a cool tidbit. Even rockets in space use the same principle for thrust. Now, not all engines are made equal. Some use propellers to push around lots of air at lower speeds, while others, like turbojets, accelerate a small amount of air to crazy high speeds. But hey, these faster engines can get pretty noisy. In today's world of aviation, you won't find many turbojets or similar engines. They're too noisy and guzzle too much fuel. Instead, smaller planes go for piston engines, while larger ones use gas turbine engines like turboprop or turbofan. And fun fact, the term turbojet used to cover all turbine engines, but now, with so many types, they're generally known as gas turbine engines. These engines have a wish list of their own. They've got to be fuel efficient, affordable to buy and maintain, powerful yet lightweight, and rock-solid reliable. And they've got to run smoothly, even under tough conditions like different altitudes or weather. To pull all this off, they need smart systems on board. Ignitions that fire up spark plugs no matter the weather, fuel delivery systems that always get the mix right, oil systems for proper lubrication, and damping units to keep those engine vibrations in check. And that's how these aircraft engines roll, turning heat into power, pushing air for thrust, and meeting the sky-high demands of aviation. Power and weight. Thrust is what moves an aircraft forward, and all power plants generate this force. While reciprocating engines use brake horsepower, bhp, as a measure, gas turbines are rated in thrust horsepower, TFP. The formula for TAP involves thrust, aircraft speed, and a conversion value of 375 mile-pounds per hour. This 375 value stems from the basic horsepower formula of 33,000 FTLB per minute, equating to 375 mile-pounds per hour. For instance, if a gas turbine produces 4,000 pounds of thrust and the aircraft travels at 500 mph, the THP calculation is 4,000 x 500, 375 ace 5333333. Calculating horsepower for each speed is essential as it varies with velocity. This makes it impractical to rate or compare turbine engines solely in horsepower. During its life, an aircraft engine operates at high power but rarely stays at maximum power for over 2 minutes. Shortly after takeoff, power reduces for a steady climb, and at cruising altitude, the engine power further drops for a sustained flight. Reducing an engine's weight per brake horsepower enhances an aircraft's performance and load capacity. Every extra pound an engine carries impacts its performance negatively. Advancements in engine design and materials have significantly improved reciprocating engines, resulting in a better power-to-weight ratio. Fuel economy. The measure of fuel economy in aircraft engines often relies on specific fuel consumption. Gas turbines are evaluated by dividing fuel flow, LBHR, by thrust, LB, while reciprocating engines use fuel flow, LBHR, divided by brake horsepower. These are known as thrust-specific and brake-specific fuel consumption, respectively. For turboprop engines, there's an equivalent measure, fuel flow in pounds per hour divided by a turboprop's equivalent shaft horsepower. Comparisons between engines can be made based on their specific fuel consumption. At lower speeds, reciprocating and turboprop engines offer better economy compared to pure turbojet or turbofan engines. However, at higher speeds, due to propeller efficiency losses, the efficiency of reciprocating or turboprop engines becomes limited above 400 mph, falling short of that of turbofans. Durability and reliability. Durability and reliability are often linked because one is hard to discuss without touching on the other. In simple terms, reliability measures the mean time between failures, while durability looks at the mean time between overhauls. Specifically, an aircraft engine is considered reliable when it consistently performs as expected in various flight conditions and extreme weather. Standards for powerplant reliability are set by the FAA, the engine manufacturer, and the airframe manufacturer. The manufacturer ensures reliability through design, research, rigorous testing, and strict control during manufacturing. Each engine is tested thoroughly before leaving the factory. Durability reflects how long an engine functions while maintaining its reliability. If an engine passes its type or proof test, it's deemed fit for regular operation over an extended period before needing an overhaul. Engine ratings don't specify a fixed overhaul interval. Instead, the time between overhauls, TBO, varies based on factors like engine temperatures, duration of high-power usage, and maintenance received. Recommended TBOs are outlined by the engine manufacturer. Engine reliability and durability are engineered by the manufacturer, but their sustained performance depends on meticulous maintenance, proper overhaul techniques, regular checks, and strict adherence to operating limits established by the engine manufacturer. These practices significantly reduce the chances of engine failure. Operating flexibility. Operating flexibility refers to how well an engine performs smoothly across all speeds, from idle to full power. Aircraft engines need to work efficiently under various atmospheric conditions encountered during widespread operations. Compactness is crucial for properly streamlining and balancing an aircraft. The engine's size and shape must be as compact as possible. In single-engine aircraft, the engine's dimensions also impact the pilot's view, so a smaller engine is preferable. This not only aids visibility but also reduces the drag caused by a larger frontal area. Weight limits are directly tied to this compactness requirement. If an engine is more elongated and spread out, it becomes challenging to keep its weight within acceptable limits. Power plant selection. When it comes to selecting the right power plant, it's not solely about specific weight or fuel consumption. There are other important factors to consider, which we'll discuss now. For aircraft cruising under 250 mil, the typical choice is the reciprocating engine. It's cost-effective and efficient at lower speeds. When aiming for high-altitude performance, a turbo-supercharged reciprocating engine works well above 30,000 feet. Gas turbine engines perform best at high altitudes, but their cost can be a limitation despite their superior performance. In the cruising speed range of 180 to 350 mph, the turboprop engine shines. It packs more power per pound than a reciprocating engine, allowing for a greater fuel load or payload. As we move higher in speed between 350 mph and Mach 8.9, turbofan engines are preferred for airline operations. For aircraft looking to hit Mach 1 or beyond, they're typically equipped with pure turbojet engines, afterburning engines, or low-bypass turbofan engines. Types of engines. Aircraft engines come in various types and are categorized by their operating cycles, cylinder arrangement, or thrust production method. These engines, whether gas turbine-based, reciprocating piston, or rotary, are all heat engines that convert fuel into heat energy, which in turn becomes mechanical energy, propelling the aircraft forward. Most current aircraft engines use internal combustion, where the combustion process occurs within the engine itself. They come with different configurations such as 2 or 4 cycle, spark ignition, diesel, and cooling methods like air or water-cooled systems. Reciprocating and gas turbine engines, they have further divisions based on cylinder arrangement and speed range. Reciprocating engines have various designs, yet some are more commonly recognized as conventional by manufacturers. They can be classified by cylinder arrangement, inline, V-type, radial, opposed, or by cooling method, liquid-cooled or air-cooled. All piston engines dissipate excess heat by transferring it to the surrounding air. Air-cooled engines directly transfer heat from cylinders to the air, often requiring thin metal fins on cylinders for increased heat transfer. Most reciprocating aircraft engines use air cooling, although some high-powered engines opt for efficient liquid cooling systems. In liquid-cooled engines, heat from cylinders goes to a coolant, then flows through tubing and is cooled in a radiator placed in the airstream. However, this system adds weight due to coolant, heat exchangers, and tubing. Nevertheless, liquid-cooled engines allow high power to be safely extracted from the engine. Inline engines. An inline engine typically comes with an even number of cylinders, although there are a few 3-cylinder versions. It can be liquid-cooled or air-cooled and features just one crankshaft. positioned either above or below the cylinders. When designed to operate with cylinders below the crankshaft, it's called an inverted engine. Inline engines have a small frontal area, making them well-suited for streamlined designs. When mounted with cylinders in an inverted position, they offer benefits like shorter landing gear and improved pilot visibility. However, as engine size increases, air-cooled inline engines face challenges in proper cooling. Consequently, this engine type is typically limited to low and medium horsepower engines found in older light aircraft. Opposed or O-type engines, these engines have two cylinder banks positioned directly opposite each other, sharing a central crankshaft. They can be liquid-cooled or air-cooled, with the air-cooled version being more common in aviation. Typically, they're mounted with cylinders in a horizontal position. The opposed engine boasts a low weight-to-horsepower ratio, making it ideal for installation on aircraft wings in twin-engine setups. It's also known for its minimal vibration. V-type engines. Cylinders in V-type engines are arranged in two inline banks set about 60 degrees apart. Most have 12 cylinders and can be either a liquid-cooled or air-cooled. These engines are designated with a V, followed by a dash and the piston displacement in cubic inches, like V1710. They were prevalent during World War II, but are mostly seen in older aircraft now. Radial engines. Radial engines have cylinders arranged in one or more rows around a central crankcase. They're renowned for their durability and robustness. The cylinders in a row can number 3, 5, 7, or 9. Some have double rows of cylinders arranged radially about the crankcase. Radial engines, with configurations like single-row 9-cylinder or larger twin-row engines, were used in cargo planes, warplanes, and crop spray planes. Despite their existence, their use is now limited due to advancements. The single-row 9-cylinder radial engine has a relatively simple construction, while the larger twin-row engines are more intricate, such as the Wright R3350 engine, with multiple sections in its crankcase. Reciprocating engines. Design and construction. A reciprocating engine consists of several key components: the crankcase, cylinders, pistons, connecting rods, valves, valve operating mechanism, and crankshaft. Within each cylinder head are valves and spark plugs. One valve controls the passage from the induction system, while the other manages the passage to the exhaust system. A piston, connected to the crankshaft via a connecting rod, moves within each cylinder. Figure 1.4 provides a visual breakdown of these fundamental parts in a reciprocating engine. The core of an engine is its crankcase, like the engine's foundation. It houses bearings for the crankshaft and supports various engine parts. It's vital for keeping oil in and letting external and internal engine parts work together. The crankcase needs to be really sturdy to ensure the crankshaft stays aligned and doesn't wobble. Typically, they make it from a strong but lightweight aluminum alloy. This part faces a lot of stress. Imagine the cylinders, which are the powerhouse of the engine, are bolted onto the crankcase. When the engine runs, it exerts huge forces trying to pull these cylinders off. Additionally, the spinning motion of the engine creates bending forces on the crankcase. It has to be strong enough to handle all this without bending too much. The front part of the crankcase can look different based on how the engine is set up. If the engine directly drives the propeller, it needs less space at the front. But if there are gears to slow down the propeller, it needs more room. So the design of that front part might vary. There's also a thing called a governor that controls how fast the propeller spins. Where it's placed can change. In larger engines, there's a small space at the front's bottom to collect oil. It's like a little oil reservoir. Because that part handles a lot of force, it needs a solid attachment. The spots where the cylinders attach to the crankcase are called cylinder pads. They're specifically designed to hold the cylinders firmly. They use special studs and rubber rings to make sure oil doesn't leak out where it shouldn't. To fix the engine onto the aircraft, they use mounting lugs. They're like the anchors that keep everything steady, especially during intense maneuvers. The engine's air system has to be tightly sealed. Otherwise, it messes up the fuel and air mix the engine needs to work properly. In the back section of an engine, known as the accessory section, they often use cast materials like aluminum alloy or sometimes magnesium. This part is where they attach the engine's extra bits like magnetos, carburetors, fuel and oil pumps, starters, generators, and more. They arrange this section to make it easy to access these components when needed. They have different methods to mount these accessories, sometimes casting the section in one piece with mounting points, or using separate cover plates made of magnesium and aluminum alloy to set up the accessory mounts. They fit accessory drive shafts onto these mounting pads, which helps control the gear ratios to make sure things like magnetos and pumps run at the right speeds for the engine to work smoothly. The gears used to drive these engine components come in different types. You have spur gears, which handle the heavier loads or need to minimize any slack or play in the system. Then there are bevel gears, which allow different angles for short shafts connected to the various accessory mounting points. For engines with opposed cylinders, the gear trains for these accessories are usually straightforward setups. In simpler terms, this section at the back of the engine makes sure all the important parts, like magnetos and pumps, get the right power and move at the correct speed so the engine runs smoothly. Crankshafts. The crankshaft, positioned parallel to the crankcase's longitudinal axis, relies on a main bearing between each throw for support. It's crucial that the crankshaft's main bearings are rigidly upheld within the crankcase. Usually, transverse webs in the crankcase support these bearings, reinforcing the entire structure. Sometimes the crankcase is split longitudinally, dividing the main bearings between sections to allow for inspection without disrupting bearing adjustments, Figure 1.6. Being the backbone of a reciprocating engine, the crankshaft endures most of the engine's forces. Its primary role is converting the piston and connecting rod's reciprocating motion into rotational motion to turn the propeller. Crankshafts consist of cranks or throws created by forging offsets into a shaft before machining. Typically forged from a robust alloy like chromium nickel molybdenum steel, crankshafts may be single-piece or multi-piece constructions. Figure 1.7 displays two solid crankshaft examples used in aircraft engines. A 4-throw construction is used in either 4-cylinder horizontal opposed or inline engines, while a 6-throw shaft is used in 6-cylinder inline engines, 12-cylinder V-type engines, and 6-cylinder opposed engines. Radial engine crankshafts can have single-throw, 2-throw, or 4-throw types, aligned with single-row, twin-row, or 4-row engines. Each crankshaft comprises a journal, crankpin, and crank cheek. Counterweights and dampers are often added to reduce engine vibration. The journal, rotating in a main bearing, acts as the crankshaft's rotational center and is hardened to minimize wear. The crankpin, attaching to the connecting rod, is off-center from the main journals and is often termed the throw. It's usually hollow to reduce weight and transfer lubricating oil. The crank cheek connects the crankpin to the main journal and sometimes carries a counterweight to balance the crankshaft. The crankshaft's type and number of crankpins must align with the engine's cylinder arrangement. Their positions on the shaft concerning other cranks are measured in degrees. The simplest crankshafts, either single-throw or 360-degree, are used in single-row radial engines constructed in 1 or 2 pieces and supported by 2 main bearings. Meanwhile, double-throw or 180-degree crankshafts are employed in double-row radial engines, featuring 1 throw per row of cylinders, Figure 1.8. Engine vibrations can lead to metal fatigue and accelerated wear of moving parts. Crankshafts play a key role in balancing to mitigate excessive vibrations. They're balanced statically and dynamically. Static balance involves ensuring the weight of the crankpins, crank cheeks, and counterweights is evenly distributed around the rotation axis. To test static balance, the shaft is placed on 2 knife edges. If it tilts during the test, it's out of static balance, Figure 1.9. Dynamic balance deals with the forces generated during crankshaft rotation and power impulses, aiming to minimize engine vibration during operation. Dynamic dampers are integrated into the crankshaft to achieve this. These dampers are essentially pendulums attached to the crankshaft, allowing them to move in a small arc. Some crankshafts have multiple damper assemblies, each linked to a different crank cheek. The pendulum moves in sync with the engine's power impulses, countering the crankshaft's vibration frequency, effectively reducing overall vibration. One type of dynamic damper consists of a slotted steel counterweight attached to the crank cheek. 2 spool-shaped steel pins extend into the slot and through oversized holes in the counterweight and crank cheek, creating a pendulum effect. Figure 1.9 provides an analogy demonstrating the functionality of a dynamic damper.